It's a pleasure to be here, and I'm really looking forward to talking to you on this topic of recent insights into how the Earth works, embracing uncertainty. I really appreciate the invitation to come speak, the invitation given to me by the Academy, and I'm particularly grateful to Professor Pat Shannon, who looks after the discourse program, for inviting me to speak on this topic. When Pat first asked me, I thought, well, maybe I'll steer a little bit away from uncertainty and just talk a little bit more detail about Earth processes. And then I realized, now this is a key topic in the national and international psyche of, people that are not working directly in Earth science. Can we predict things? If not, why not? And I thought that even though it's not specifically my research area quantifying uncertainty, my research area is around the context for uncertainty in Earth systems. So that's what I'm going to do today. I'm going to give you the context for the uncertainty in Earth systems. What I'm not going to do is talk about the quantification of that uncertainty in any great detail. And for people that are in the academic side, I'm pitching this at a level of a public a presentation to the general public. So there will be some detail missing in that regard. So. I'd like you to think of the last time, or the last few times that you drove to work. If you were really unfortunate, it looks something like this, okay? And you're sitting in the car going, and here I go again, and I promised myself that I would never do this, but here I am. And then the next day you go out and you drive on the same road, and it looks something like this. Which is kind of confusing because it's not clear what the difference is between day one and day two, except the traffic. So, but everything else looks the same. There's no special event on, there's nothing unusual on, but the traffic is really bad on day one and not so bad on day two. So I guess we've all been in this situation. And then I'd like you to think about something different. I'd like you to think about the last time that you went cliff jumping with your friends, okay? For some of us, that's a long time ago, but for others, thankfully, there are some younger people in the audience, it's not so long ago. And the question I'd like you to think about is, did you take a chance with the water depth before you jumped into the water? And of course, the answer is, if you're under 23, yes. But if you're over 23, no, you didn't. You would actually plan this event with your friends weeks in advance, and you'd looked up the tide tables, and you knew exactly when the high tide was. So in that regard, there's something completely different about this system here that determines the tide and the system that controls the traffic. So not all systems on the Earth are the same. And so we will address that. We will look in a little bit more detail about what's different. Okay, so we want to talk about that uncertainty, and the question is, where does that uncertainty in problem one with the traffic come from? And in problem two, there doesn't seem to be any. But we'll come back to that in detail. So what do I mean by uncertainty? What we mean by uncertainty is not our inability to measure something really precisely. The weighing scales doesn't have enough decimal places, or you can't quite see the thing properly because it's a little bit too far away. That's not what we're talking about necessarily. That's measurement uncertainty, and we have that all the time. But it's not the driver for what we're really after here. What we're after is uncertainty in the physical system, so that we're uncertain about what the physical system will output. We do something in the physical system that we're involved with, be it driving the car, be it doing something in earth science, and there's uncertainty in what happens. You're driving the car, how much traffic is there? You're doing, you're waiting for the next earthquake, you're waiting for the next volcanic eruption. There's uncertainty in when it's going to come. That uncertainty is inherent to the system. It's not actually a measurement problem. So I just want to clarify that. So we can think of the traffic situation as a kind of a system uncertainty rather than a measurement uncertainty. Some of us are very afraid of uncertainty, of course, and we crave certainty. And that's something that science probably didn't do itself very many favors with over time. We kind of sold the idea that science was able to predict things. That's what scientists do. Scientists predict things. And what I hope to show you today is that that's not actually what science is necessarily about, predicting things and reducing uncertainty down to zero. Uncertainty is something we possibly will have to live with. And I'll show you, I think I'll show you that as time goes through. So some people find it annoying, some people find it enriching, but if we're not careful, if we get it wrong, it can actually be lethal. So here's an image from the tsunami, the Tohoku earthquake in Japan in 2011, and you can see the tsunami is just arriving on shore. And this was absolutely lethal for hundreds of thousands of people. And I guess the question is, how in 2011 can something like this happen? Like, we think we're on planet Earth for quite a long time. How do we not know what's going to happen at the level that so many people can get caught out in this scenario? What actually happened here, if you think of also in a country like Japan, Japan is so well engineered with respect to protecting people. If you've been in Japan and you see the coastal area, it's heavily engineered with defense walls for tsunamis and so on, and yet this can happen. What happened here primarily was uncertainty in the details of the size of the earthquake. So it was known that this region was very dangerous, and tsunami walls were in place. It's just that the actual size of the earthquake caught everybody by surprise. It was much bigger than had been anticipated inside the bounds of what might occur, and it actually swamped the tsunami defense infrastructure and caused the damage that we're very aware of. So the problem here is the uncertainty in the system. It's a systemic uncertainty in terms of how big this earthquake was going to be. And I hope to show you why things like that can happen. So in order to be able to do that, we need to roll back and ask the question, actually, how does the Earth work in general? Because without understanding, we might start with the premise that without understanding how it works, we can't really predict. And then we might change our minds on that later, but at the moment, we'll take that viewpoint. So we're living in absolutely fantastic times of discovery. I mean, we think about it as a great age of technology, but also in terms of Earth and space physics. This is an amazing time to be alive. It might surprise us to think that the notion of the sphericity of the Earth was only really properly settled when Magellan sailed the globe in 1521, and it came around the other side. And then people went, definitely, it's a sphere, okay? Plate tectonics that we take for granted now was only really settled in the late 1960s. So we were actually sending people on the way to sending people to the moon, and we still didn't know how the Earth worked. And I don't mean the details, I mean just the big picture. How does the whole thing fit together? Okay, so it's a very, very new discipline, okay, in that regard. So it's a great time. It's a great time for discovery. So what does planet Earth look like? Or the inside of a planet look like? Well, there is no one size fits all. This is Earth. And it's mainly rocky planet. So it's got a rocky inner core, it's got a liquid outer core, it's got a rocky mantle, and it has a crust, a thin crust at the top there. So if you look at, say, Jupiter, for example, it's different. It's got much, relative to its size, a much smaller rocky interior, plus then it has a molecular hydrogen around the edge. But we're going to focus on, so there are many different types of planets. So we're going to focus on planet Earth, obviously, because that's what we're talking about here. And so what we say here doesn't necessarily apply universally. It applies to planets that are working like our planet. And one of the things we need to realize is that although we have a rocky mantle, that rocks can flow. That's a key point. That, you know, something that looks solid sitting here on the table, if you put a gypsum on the table at room temperature or above room temperature, and you just go off for a few months and come back, it will flow away, just like tar on the street, okay? So there's a rock that actually flows, and the time scale is really important. So over long time scales, the rock is actually flowing, but at short time scales, it behaves like a solid. So the fact that rocks can flow actually that's the engine, that's the consequence of the engine for plate tectonics. So that's the broad scale picture. We might call that in science terms the first order picture of what the inside of the Earth looks like. But the details actually matter. So let's go in and zoom in a little bit more and see what the details look like. Now this is a picture of the chain. This is a cut into the Earth. So you're looking inside in the Earth here. And this is a picture of how the speed inside of the Earth is changing from place to place, the speed at which waves travel. So if I tap the table, waves travel through the table. But if I hit the ground harder, if there's a big earthquake, waves travel through the ground, and they travel at different speeds in different places. And the speed at which they travel is controlled by two things. One is the rock type, what type of rock, but the other is the temperature of that rock. So what we're looking at here are primarily temperature differences inside in the Earth. And those temperature differences are really important. Where do they come from? Well, there's some original heat from the formation of the Earth due to frictional heating when the Earth was forming, but most of the Earth's internal heat is coming from radioactive decay. So but those temperature fluctuations are important because they drive plate tectonics. Because once you got those temperature differences from point A to point B, things start to convect. If you look into your porridge in the morning and you heat one side of it on the cooker, you can see the stuff convecting from the hot side over to the cold side. So once you have these temperature variations, you initiate convection. And that convection drives plate tectonics. And we all know, every school kid knows about this. But this is actually an incredible story, really, because what's happening, when we look at the Earth, we think of the Earth as looking like this, but it doesn't really look like that. It only looks like that now. 60 million years ago, it looked completely different. And in 60 million years' time, it'll look different again. So our biological clock is running very, very fast relative to the geological clock. So we've arrived on Earth, we've taken out our camera, we've taken pretty much a single snap with a bit of a smudge in it, and then we've gone away again, okay? And the geology is doing its own thing. So we're taking that snap, we're trying to understand what's happened in the past and what might happen in the future. And then digging into various aspects of the legacy that's left on the Earth in terms of past processes. So this is what the Earth looks like now. But we now understand how plate tectonics work. So we think that when we look at the world, we'd be able to say, okay, we can predict how things are going to happen, because for the first time over the last 40 or 50 years, we have a framework for how the Earth works. I love this image because it's basically a topography map. So we've taken the Earth's water off, and you basically just look at the different aspects of the Earth. You've got the continental crust, which is the kind of light stuff, like boiled, that kind of frothy stuff that went to the surface, silica rich. Then you've got the basaltic stuff, which is heavier. The reason it's lower down is because it's heavier. It's just sitting lower. And you take the water off. So this is called oceanic crust, and this is called continental crust. But the oceanic crust doesn't have anything to do with the ocean per se. It's only called the oceanic crust because it lies below the water. And why does it lie below the water? Because it's the low ground. So if you pour the 1.3 billion cubic kilometers of water on planet Earth back on here, it'll just fill up the low ground, okay, which is all of this area here. But to be able to strip it back and see it like this, we get an idea of how the Earth works. We can see the mid-Atlantic ridge, where we get the crust is expanding, and we can see these zones, and I'm going to talk about these zones here, where the crust is actually, the oceanic crust is going in underneath the continent. And these are zones where we get lots and lots of earthquakes. And so in Japan, it was over here, you've got this trench area, and the Tohoku earthquake was related to that, and the slippage then that caused the tsunami. So we want to understand, why are we not able to predict these earthquakes? So we've seen that there's an uncertainty in some earth processes. We've seen that already. But we're confused because we have a broad understanding of how the Earth works, so we don't know why we're not able to make these predictions. So the next thing I want to do is I'm going to have a look at three ideas. And the first idea is the idea of prediction. The second idea is the idea of forecasting. And the third is a really exciting development. It's the idea of early warning. And there are three distinct things. Now, not everybody, maybe even in the room, will have the same, will agree with me on these definitions. There's some debate about them, but I will explain what I mean by these things. So we will use earthquakes and volcanoes as an example, but the concepts apply to landslides, glacier breakup, even to atmospheric physics in terms of how the system, broadly how the system works. So prediction, what do we mean by prediction? So what I mean by prediction is that we can say with a level of certainty that something is going to happen in a particular place at a particular time, or within a very, very short time window. So, for example, is there going to be an earthquake in the Midlands tomorrow in the late afternoon, or tomorrow at 6 o'clock or something like that? That's a prediction. It's like if I said there was, I hope this is not streaming live, then that would be a prediction, okay? But the time window is very, very short. it's very prescriptive, it's very, very precise. And this has been the kind of holy grail of earthquake physics for a very long time, until relatively recently, until the last few decades. People thought, hey, we know how the Earth works now, so we're going to use that knowledge to predict. And that really started back after the 1906 San Francisco earthquake that everybody will have heard about, with an idea called the elastic rebound theory. And the idea there was, if you imagine this, this is the Earth like this, so that's a fence there. And there's a real fence. You can see it, just about see it. It's the lights. It might be difficult to see with the lights, but there's a fence. And the idea, there's a fault going in this direction, so a geological fault. And the idea is that as the Earth's mantle is convecting, remember I said it convects because of that temperature variation, it pulls those two sides of the fault together, but they're kind of stuck together because of compression. And they're trying to slide past each other, but one side bends and the other side bends, and there's no slippage on this fault. This is the classic idea. But once there's enough stress such that the frictional strength of this can't hold anymore, then the thing slips and you get an earthquake, okay? And the idea was, well, mantle convection is pretty consistent, pretty constant, so the thing should be just kind of rolling along like some sort of clockwork, and then every so often we'll get an earthquake that were called characteristic earthquakes of snap, stress buildup, snap, stress buildup, snap. And that idea, which at the time, was a very good start, of course, this is way back after the 1906 and developed from that, it led to a very detailed earthquake prediction experiment in Parkfield in California. And what had been noticed is that you have these repeating earthquakes. There's one there. This is year. This is 1840, and this is the year 2000. And this is just event number. So this is just an index, just counting the events. So you have an event here, and then somewhere greater than 10 years later, you have another event here, and then another event here, and another event here. And people noticed, hey, we've got these repeating events. Not only did they repeat in time, but when you looked at the seismograms, and I'll show you seismograms later, the wiggly bits, they kind of look the same, the wiggly traces. So we thought, hey, this is a great place to look at how earthquakes are actually forming. And so a huge amount of infrastructure was put in this area around Parkfield, which is a small town in Southern California, to wait for the next earthquake, which was coming in 1993-ish, with some very small window around it, okay? They spent a lot of money, they waited, and they waited, and they waited, and nothing happened. But fortunately, they kept the infrastructure running. It had strain meters, seismometers, all sorts of instruments for measuring what's going on in the ground. And eventually, the earthquake, and then there's debate as to whether it is that earthquake or not, the one they were waiting for, came in 2004, 10 years late, okay, if you want to call it late, which is a huge error on events that were occurring just over a decade or 15 years apart, okay? So it was a very interesting experiment, and one of the proponents of the experiment said afterwards in 2005 that reliable short-term earthquake prediction is still not achievable. Now today that might look like it was quite a cavalier thing to do, to put all that infrastructure in to try to track something like this, but you think back then this was the way things work, and we were trying to capture it. The idea was to capture that earthquake as it came. So the question is, what happened? Why did, and by the way, the San Andreas system in relative terms is a relatively simple system. I mean, in terms of how earthquakes work. And it's the most monitored system in the world in terms of its simplicity, complexity ratio, if you like, or equipment ratio. So basically, it's still, even in that simple environment, we just ran aground, ran foul. So why? So it's become apparent that the reason that this happened, by the way, this is not a picture from Monaghan, although it could be. I think it's actually smaller than Monaghan, is it? For those of you who don't know, there was a mine collapse in Monaghan yesterday, the day before. An old mine, by the way, that's well out of use. This is in southwest Kenya, and this is an amazing part of the world. So for a whole bunch of reasons that we won't go into, but this is where a new, and let me just go back here and show you if I can do that. So we have a new ocean probably in the future forming here in the East African Rift, the cradle of civilization, the cradle of human evolution here. there's a new opening. So this is a rift valley. It's actually being pulled apart. It's generating, the fantastic tectonics here are generating multiple habitats for biological evolution, and it's an incredible place. And so it's pulling apart. And this is an example of it pulling apart. But here you can see part of the reason why prediction of the system could be quite difficult. If I just imagine, let's imagine we want to, this is being pulled apart like that, but let's imagine that we want to actually, just for argument's sake, just compress it back together again and then slide it along to try to figure out, just slide it along to try to figure out what happens. If we try to compress that back together again, what you'll notice, if you imagine my two hands are either side of that fault, that they won't fit back together properly. They kind of touch each other, but they won't fully fit back together, okay? So now, as I try to slide it, a piece of my hand will slip, but the other bits around it won't slip. And then as they slip, they will actually lose their stress. And where will that stress go? Well, some of it will go away as a wave, but some of it will actually load its neighbors. And then the neighbors will load their neighbors. And so the system seems to be kind of unstable, almost like a kind of a domino. So this is better seen in this image here. If we imagine that this is one side of the fault and this is the other side of the fault, it's on the wrong direction. Let's imagine that we just bring it and we pull it together and we clamp it together like this. So this is a classic nonlinear system called cellular automaton. Let's say imagine that this breaks. As we go to slide these plates, this guy breaks. What will happen? The stress that this guy is holding will have to go somewhere. It'll get passed to its four neighbors. And then we ask the question, what about this neighbor? How stressed are you? Have you reached your predefined failure criterion that you can't hold any more stress? And if the answer is yes, you will fail and you will trigger failure on your neighbors and so on and so on. A system like this can produce no events, almost no events if something slips. So this guy can slip. In other words, it can slip and pass very little stress to its neighbors, or it can slip, pass very little stress to its neighbors and they do nothing, or it can slip and pass very little stress to its neighbors and then the next neighbor goes, the next neighbor goes, the next neighbor goes, so you can have an arbitrary size event. So the problem with this is it's very difficult to say what's going to lead to an event of arbitrary size. Even one tiny little failure can give you an event across the entire system. Where is the problem coming from, or the issue coming from? The issue is coming from what we call heterogeneity. Variability in the mechanical properties of the medium. So again, if we press this together and try to slide it, there's a lot of variability and heterogeneity, and the bits are interconnected, and so if one bit fails, it'll pass all that stress to its neighbors, and they will pass to their neighbors, and so on and so on. So it's very, very difficult to predict in a system like that. If you look to the right-hand diagram, this gives you an idea of what sort of events this system generates. So here's the size of the event, and here's the number. I don't have too many of these diagrams, but I'm just going to show you this one. And what you can see, and I won't go into the details, you can see this is what's called a scale-free system. So in other words, in that lattice I showed you, you don't get events of an average size. You get lots and lots of tiny events, as you might imagine, where just one cell fails or two cells fail. And you get very few, very large events where the entire lattice fails. But there's no average amount of events that fail. There's no scale in this system. Okay? So this system is in a sense, it's scale-free. It's only bounded by the smallest cell you have and the size of the whole grid. And it's a hallmark of what are called critically unstable systems. So they're at the edge of failure all of the time. Minor perturbations can cause catastrophic failure in a system, critical instability. That's the numerical model. This is a numerical model, by the way, computer model, computer model, this. This is the output from the computer model, and this on the left is a classic, what's called Gutenberg-Richter, or magnitude frequency distribution for earthquakes. This is the magnitude, you can see this anywhere in the world if you measure earthquakes. This is the magnitude of the earthquakes. This is just starting at magnitude 4, going to magnitude 7, and this is the number of earthquakes you get. You get a lot more magnitude 4s than you do 7s, and you get more 5s than you do 7s, more 6s. And you can see the shape of this curve is very similar to the shape of that curve. So basically, this type of statistic is also the hallmark of a critically unstable system. So it doesn't nail it completely, but it's an indicator that earthquake physics is behaving something like, at least it has the same outputs as a system that we know is inherently unstable. okay? And that instability is coming from the heterogeneity. If you do the same for the size of volcanic eruptions, you see the same patterns. So it's very difficult to say in advance if this holds up, how big a volcanic eruption is going to be, because it looks the same way. So there's no information in the system about the size of the next event. So other examples, so that's like computer models and a bit of data, but what about real examples of sensitivity, what we might call system sensitivity? When I first saw this paper some years back, actually, my mouth was wide open, that a typhoon could trigger an earthquake. Now, on this is not a small earthquake, these are big earthquakes. The difference is they're very slow. They don't go bang, they go slowly creeping. But when you add up all of the energy released, they're actually quite big. And I'll talk to you more about slow earthquakes later. And the reason that typhoons are able to trigger slow earthquakes is because of the pressure changes in the Earth's atmosphere. So as a typhoon goes by, you get a pressure drop. Okay, so you think about a fault in the ground like this. So here's the fault, and it's trying to move. But on top, you have the Earth's atmosphere is pressing down on the Earth's surface. Okay, now let's imagine the fault's trying to slide. But if you reduce the pressure of the atmosphere, it kind of unclamps the fault a little bit. There's not so much pressing down on the fault anymore. So the fault is trying to slide sideways, but it's been clamped. But if you reduce the pressure, then the clamping is reduced, and then just if you got the shearing is the same, then it allows the fault to move. So just as the typhoon goes over, the normal stress, as it's called in geology or geophysics, the stress perpendicular to the thing is actually reduced, and the thing slips, and then when the typhoon stops, it just reclamps again. Okay, so that demonstrates that you've got extreme sensitivity to the stress field and the material properties. The thing is on the edge of failure all the time, and that an actual typhoon can trigger it. We were fortunate enough to be invited to a really, really nice experiment in the Galapagos Islands earlier this year, and with the University of Edinburgh and the Instituto Geofísico in Quito in Ecuador. And one of these projects was actually to look at sensitivity, and I'll show you the diagram that drove the experiment. So this is the network we put in, just for detail. So here's this South America's here, Galapagos, I can't really see that from here. Galapagos is over here. And so what I'm going to show you is seismograms from an earthquake just off Honduras that's passing it's about 1,000 kilometers away, and the waves from that earthquake are passing through the Galapagos Islands, okay? And I want to show you something on this volcano here, which is Sierra Negra volcano. It's on the southern part of Isabella Island. This is, I'm not sure if this is Martin or one of our French colleagues, but this is an installation. I'll show you a picture of Martin later. He does a lot of our fantastic field work. So that's one of our installations there in the Galapagos. So this is the event. And so these are the wiggly traces associated with the earthquake in Honduras. They have traveled 1,000 kilometers in the subsurface, in the ground, and are now going right through the volcano in the Galapagos Islands. So this is the main event. These are just the earthquake. But if you take this is called some very low frequency waves that are coming all the way from the big earthquake. If you take this and you filter out all those low frequency waves and you just look at the very high frequency waves that are in the data, you can see something really, really interesting. Here's the event starting in this is the event arriving from Honduras. This is a thing called a P wave. It's the first wave to arrive, and you can just see it there. This is the S wave, the second wave to arrive. And as soon as these other waves that travel across the Earth's surface, they're called surface waves, so the P waves and S waves go down into the Earth, and the surface waves travel across the Earth. As soon as they arrive, you can see a whole bunch of really, really high frequency, little local earthquakes are triggered on the volcano. So here we have an earthquake 1,000 kilometers away, and when these waves come rippling across the Earth's surface, they actually trigger failure, earthquakes on the volcano itself. So that proves that the volcano is highly, highly sensitive to very small stress perturbations. Now that was prior to the eruption. There was an eruption on the 26th of June. This effect disappeared after the eruption. So what it says is that the volcano, just prior to the eruption, was critically stressed, and the tiniest little bits of extra stress were enough to make it fail. Now I want you to think about predicting in a system like that. I mean, even our common feeling for what that would be like, that, if you touch it, it might break. The kind of straw that breaks the camel's back. It's very hard to say, can you put another straw on? It's very hard to say when to stop, okay? So it's hard to say when the thing is going to fail. So, some key interim conclusions on prediction. Earthquakes, repeat times, do not behave like clockwork. They're not going tick, 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 through, using this elastic rebound model. So it doesn't make sense really to say, hey, the big one is due now. It just doesn't work, okay? It doesn't work. They're not that regular that we can say, base on the timing, we can say, okay, now is the time. It doesn't really work like that. The earthquake system seems to be, or as close to being, critically unstable. So it implies it's very sensitive to small perturbations in stress or strength, and it implies the outcomes are uncertain. So we need to we need to look at the problem from a different direction if we're to chase down the holy grail of certainty and the holy grail of, say, earthquake prediction, volcanic prediction, landslide prediction. They're all related in terms of the physics of the problem. So what is that? That is maybe to look in more detail at the seismic signals that emanate from a volcano, from an earthquake, and so on. So how do we measure seismic signals? Well, it's a little bit more sophisticated than this, but this is the basic principle. You have a spring and a pendulum, and the ground moves, and in fact, this actually works the other way. The ground moves, and then the pendulum, the spring more or less stays where it is. And there's some measure of how much the spring is moving. Is what you record as the seismic signal, okay? So that's how we measure the ground vibrations. And the idea here is that when things are going on inside in the earth, things are breaking, they send out sound waves as they're cracking. Just like if you took a ruler and you cracked it, it sends out a sound wave. And those sound waves are picked up. And the idea is that we try to say, what is happening in the earth that made that sound? So it's kind of an inversion problem. You're taking the data and you're saying, what made that sound? Now, that might seem fairly straightforward, but it turns out to be quite complex in terms of the Earth. And again, it's related to heterogeneity inside in the Earth. So what do these waves look like? They're not necessarily just sound. There's sound wave propagation in the Earth, but they're very complex because as I'm speaking here, you're listening to acoustic waves. But inside, they're just pressurizing your eardrum. But down inside in the Earth, we have many different wave types because the Earth has what we call a shear strength, so it can support a lot more waves than the air can support in terms of propagation, which makes wave propagation in a solid Earth much more complex than wave propagation in water or air, for example. So this is a typical example. This is an earthquake in earthquake studies. This is a magnitude 7.3 earthquake. It was August 21st from Venezuela, and it's recorded on the Irish National Seismic Network. You can look at this website, gives you some more information about the network and other things that we recorded. And this is all the stations around Ireland. The faraway stuff I can't see because of the light, and the near stuff I can't see because I don't have my glasses on. So I've arrived at that age, I guess. So the top one is Kerry, Galway, Wexford, Dublin, Donegal, and Louth. And so you can see these stations all record this wave coming in. But there's a key thing I want to mention to you about this. There's a kind of a pattern to these waves. And this is the point, because when I'm going to show you later, this pattern is missing. And that turned out to be an exquisite observation in terms of us understanding a little bit more about how the Earth works. This is the standard stuff of how we understood the Earth works, or how earthquakes happen. So when an earthquake breaks, you get P waves. The details of how they work don't really matter. They travel, they're compressional waves, they travel fast. Then you get shear waves that do this, and then you get these surface waves that go around the surface of the Earth, and they have this sort of motion, okay? And they're the things that cause a big damage at earthquakes. But they travel at different speeds. So the first one there, the P wave comes first, the S wave comes next, and the surface wave comes next. So you can see a nice pattern. When you see a regular earthquake, you'll see some P waves, then after a while you'll see some S waves, and you'll see some surface waves. And by the way, the delay time between the P wave and the S wave is related to how far away the earthquake is, because they travel at different speeds, those two wave types, okay? So that's what we expect in a classic world when we're looking at earthquakes. However, recently there have been absolutely amazing discoveries in earthquake physics. So here's an example. It's a little bit complex, but this is in a subduction zone. So this is northwest of Canada. So one of these zones where the plates are coming together. And you can actually see this is This is the displacement or the distance, basically, that a GPS receiver is moving. A GPS receiver isn't just for telling you where your car is. You can actually use it in science. If you put a well-controlled GPS receiver on a plate, you can actually measure the plate moving at about the speed that your nails grow over the years, just by looking at how fast the GPS station is moving, okay? So we can actually see plate tectonics with technology. And it's not just like simulations. We can actually track plate tectonics with technology. So here's the plate moving. Okay? And then suddenly it goes back in the opposite direction. So it's moving in one direction, then it slips back. And it's moving again, and it slips back. And it's moving and it slips. And you can see with these events, these were not noticed before until the GPS systems went in. And then some people in Japan put in some highly sensitive seismic recording instruments in boreholes, and they saw these beautiful tremor signals associated with each time this thing slipped back. These signals are very, very different to what we've been used to seeing for earthquakes. And then people in Canada went looking for the same thing, because now they're looking for the same thing. They could find it in regular data. Why didn't they find it before? Because, you know, the rules said that you filtered the data like this, and then you did that, and and by filtering the data like that, you were throwing out some of the coolest stuff that had been seen in 50 years, okay? But anyway, they went back, found it, and these are these tremor signals. And they're continuous signals of signals like this. They're not going boom, 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 like regular earthquakes. They're just kind of grinding away, okay? And they're revolutionizing our understanding of how earthquakes work. These earthquakes are very large. It's just that they're very slow. So if they happen very quickly, they would be seriously dangerous. But they're happening quite slowly. So dynamically, they don't generate a lot of waves, but when you add up the amount of energy they've released, as I mentioned earlier, they're quite large. However, the problem is that these guys, like the model I showed you before with all the cells, the cellular, these guys are stressing up their neighbors. They're stressing up the neighboring faults that do break quickly. So every time they move, they're giving these nearby guys a little bit of a nudge, pushing them closer possibly to failure. Not all of them. Some of them, they're pulling them away from failure a bit, but some of them, they're pushing closer to failure. So they are dangerous in that regard, but we can track them using this tremor stuff. Okay, so this is a very busy slide, but I'll show you what I'm trying to do in a moment. So this is a tremor signal that I just showed you, but this is a zoom of tremor on a volcano. And the weird thing about these signals here is we only ever thought that we could see these signals on volcanoes before, this tremor signal. They had been seen on volcanoes, but on volcanoes they were thought to be related to fluid flow. But we've no fluid flow in the environment that's now known that I've shown you for earthquakes. So here we have a whole new understanding of what causes these signals. So if we want to look at this tremor and try to understand it, how do we go about understanding it? And it's a very complicated looking signal. So people have tried to draw analogies with music with these signals, okay? So I won't go into the details of this in the interest of time, but basically, if you have a string, a piano, a guitar string, you pluck the string, you end up generating a fundamental frequency, and you end up generating harmonics, higher octaves within that, okay? With that string oscillation. You can kind of hear the higher octaves as well, higher harmonics. If you have an instrument like a bassoon or a panpipe where you have one end closed and the other end open, you end up producing different types of sound, like odd harmonics. So different instruments produce different types of sound. So people have been thinking about music as a way of understanding this. So the thing is, here's the spectrogram for this tremor. What does that mean? This means if you look along here, this is time increasing, and this is time increasing along here. If you look along here, you can see, this is frequency up here, you can see the different vibrational frequencies that are in this signal, like as if it was a piece of music. So if you pluck the string, you can see the string vibrating, and then you can see that plotted, the frequency of that vibration plotted here. Except this looks incredibly complex relative to what you would expect if you just plucked a string. Okay, so this here is just a snapshot for people that are interested in how plucking a string should work. So what I did was something a little bit maybe mad, but I just decided to do this. I just decided to convert this spectrogram into a few chords of music, just to give you an idea of how complicated the thing sounds, okay? So what I've done is basically said, okay, here's the frequencies that are in this. If it was just a string, and the fundamental frequency was 1 hertz, then I would expect to see 1 hertz, 2 hertz, 4 hertz, 8 hertz. When I look at this, I don't see that. So if I just pluck the string, I would expect to see 1, 2, 4, 8, but I don't see that. I see multiple frequencies, okay? So there's something else going on. It's not just a nice, clean instrument. It's some sort of a weird creature that's producing some very, very strange sounds. So hopefully, have a listen. Okay, I feel like I'm back at doing my grades sight reading exam here now. Okay, so I'm going to forget about the rests. So what I did is I took 4 slices from here. Took 4 slices, and I said, okay, what frequencies are in each slice? So that's a time sequence. Bum, 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 bum. Okay? And you think, does that sound strange or does it sound odd? If this was a plucked string, it should have just sounded like this. If you look at the fundamental, the bottom one is actually drifting in time a little bit. So even if we take that into account, so this bottom frequency is drifting in time a little bit. So if this was a nice, well-behaved instrument, it would actually sound like this. That's what it should sound like if it was behaving itself properly. But actually, it's actually doing this. So what's my point? The point is that these are very, very complicated signals. And so to try to turn the signal I showed you here into a process inside in the Earth is very tricky. I mean, if you heard that, it's very hard to know what's going on. Is it like multiple, is it behaving like multiple instruments? It's certainly not behaving like one instrument. There's no one instrument that can produce that by plucking it, by hitting or plucking a single string or blowing into a single reed. It just couldn't be done. You needed something like a piano to do that, okay? So the point is that they're very complex. So the conclusion on prediction is I suggest that we still do not know how all of the components of the system work in sufficient detail for us to use this for deterministic prediction, to say exactly when and where something's going to happen. Now, I should say there's a hint that this might not be true for specific volcanic environments, but I'll come back to this. I'm a little worried about time here, but I'm still going to play you a little bit of sounds. This is not the same sound we had before. Hear the stuff in the background, the crackling. Challenge as a geophysicist to try to figure out what that means. So that's the challenge, okay? So it's a job for life. Okay, so I've talked about prediction. Now I want to go on and talk about forecasting, which is not the same thing. And we need to distinguish between forecasting and prediction. I see Peter Lynch down here, so Peter, you can correct me if I'm wrong about anything to do with forecasting. So forecasting includes an inherent uncertainty in what will happen in individual cases. So when will the next big earthquake happen? When will the next volcanic eruption happen? When will the next storm happen? So what forecasts do is they tell us, on average, they give us a sense of what's likely. And this is called probabilistic forecasting, but they don't tell us about specific events. So I'm going to try, although I'm not a weather forecaster, I'm going to try and maybe give an example that might not be completely accurate, but we'll just run with it as an idea. So let's say, for example, and we don't do it in Ireland, but in the US in some places they do. Let's say, for example, the weather forecaster says there's a 20% rain tomorrow, a 20% chance of rain tomorrow. And it rains cats and dogs the next day. And everybody's on the street going, I told you, weather forecast, wrong again, okay? Why is it wrong? Because it's only a 20% chance of rain, okay? But the point is that in order to understand whether the forecast is working properly or not, you cannot do that on the basis of one observation or one realization. You'd need to run that experiment hundreds of times to see, on average, does the forecast get the right amount of rain, it does rain or it doesn't rain. So basically, there's no direct information about an individual event with certainty. And this is a real challenge that we have to deal with in society, with the way we actually approach this problem. We have to look at the uncertainty around something like a forecast, rather than assuming that it's telling us with certainty what's going to happen. So what about in earthquake systems? Do we have the same thing? Well, we can do that. We have the ability to do that in earthquake systems as well. If you look at this diagram here, the one I told you about that suggested that the system was critically unstable, you can actually use the amount of small events that you had here in the past to estimate how long you're going to have to wait for a big event over here. So, for example, you can take the slope here like this, and if you were down here, you can see how long you have to wait. As you fill up, if you wait longer, this goes up and up and up because you get more and more and more events. And if you still haven't had a magnitude 8 earthquake here, you can use this slope here to project how long you have to wait on average to give yourself a magnitude 8 earthquake. So there's information in here about what is likely to happen or how long you have to wait, just in a simple diagram like that. It doesn't tell you exactly when a magnitude 8 will come, but it does tell you how long you might have to wait. So there is forecasting information in there. So this is a real drive in earthquake physics and volcano work now, is to look to forecasting and not to look to prediction, to get average properties of what's likely to happen over particular time windows. So there's a 60% chance of a magnitude something earthquake in this region in the next 30 years. That's the way that the discipline is going, not saying we're going to have an earthquake at a particular time tomorrow. Okay. The other thing, final point that I want to talk about in this trilogy of points before I move on to just say a little bit about modeling and then finish up, is early warning. Early warning is a really interesting approach that allows us to warn of an event that is already happening. Now, it might seem a bit crazy. What's the point in warning about an event if it's already happening? But the point is, if that event is some distance away and still hasn't reached the people it's going to affect, this can be extremely useful. So a good example of early warning, what I would regard as early warning at least, is the weather system, again, is weather radar. It's a physical detection of rain in the atmosphere. It's not a rain forecast. I'm not saying it might rain here. You know it's raining there, and the question then is, the only uncertainty is, will it continue to rain, and how long will it take to drift to you, so anybody who's cycling, I guess, looks at the weather radar all the time and figures how long it's going to take to get to you, okay? That's a very, very useful approach, because you're not trying to forecast the event, you're measuring the event, and you're then using that to give yourself some sort of early warning. Other good examples of early warning include pipeline shutdown, transit shutdown, critical data center shutdown. But how is this done? So in an earthquake scenario, if the ground starts to shake associated with an earthquake, the waves for the earthquake are probably traveling at 5 kilometers per second, or maybe 6 kilometers per second. This is quite fast. The shaking waves are traveling from the earthquake out into the countryside. But if you can pick up that earthquake with a strong ground motion sensor or something like that, and then send the information to the critical infrastructure, you can shut down that critical infrastructure in advance of the waves arriving, for example. Data centers, trains, gas pipelines, and so on. So this has become a really interesting area. It's very, very heavily dependent on communications technology and real-time data analysis. And I'll mention that later on how that works. So I'm going to show you a little bit about our early warning that we're trying to develop for volcanoes, and I'm going to play another sound file as I'm doing it. Hopefully you can hear it. It starts to crackle. I haven't time sequenced this with the plot, but I'll talk through it at the beginning. So basically what I'd like you to concentrate on is this top diagram here. This is depth. This is Piton de la Fournaise volcano in La Réunion Island. So this is depth. So is the file playing? It is, yeah. And this, forget about these two. This is kind of like the XY position. So this is just the depth of this signal. So we've used, they have a really good network on Piton de la Fournaise, and we're actually locating where all of this noise is. We're locating everything. We're just locating where all of this noise is, okay? And you can hear it's crackling away. And we're in here somewhere now with this crackling. We're just in here. And so this is depth. This is the Earth's surface, the top part here. If it was that high up, so the volcano is actually sitting above sea level. So this is going from zero here to above sea level here, to a couple of kilometers above sea level. So we're listening with the instruments, and stuff's going on underground, and we've got multiple instruments, and we're actually recording. We're figuring out, we can do this in real time. Although this isn't a real-time example, but it can be done in real time. Where is this noise coming from? And now we're moving in here. It's crackling away. So this is magma flowing in the subsurface. It's breaking the rock, and it's flowing through. So the magma is cracking. The rock is cracking open. You're literally fracturing rock in the subsurface to break through on your way to the surface, okay? But this is the key bit that we discovered, not only here, but I'll show you later in Iceland, is that it's broken through, and then it effectively goes quiet. And you think it's all over. What was all that about? But if you track that noise in detail, you can actually see it's rising to the surface. That tiny bit of noise, it's very, very quiet. But it's rising to the surface at about 2 kilometers per hour. So you have lava, or magma, which is going to become lava, pretty much thundering its way up from 2 kilometers depth. It's on its way up to the surface, and everything's very, very quiet. Except if you track this stuff, you can see it. And then, hopefully very soon, we'll hear something completely different. Hear like a jet engine coming. So it's just arriving at the surface now, after that quiet period. 1 minute here is about 1 hour, so there's an hour thing. And now you can see, this is the seismogram from it. Now we've got lava flowing on the surface. So the two things we've here, we can actually say, when this break finishes, how long it'll be before that magma lava arrives on the surface. And actually, one of the big issues with volcanic eruptions is they're often volcanoes that are in remote places. We don't know when the eruption actually started. You can actually say that's exactly when the eruption started. But you need good technology here, very good sensing network. You need rapid data analytics to give you the information you need, and you need a very good communication system. And there's a third thing you need, which I'll talk about. There's a social side to this as well, which we haven't talked about yet, but that's also very, very important. Okay, so we've also done this at Bartabunga in Iceland, and I won't go into the details. I'll push on, but we found the same thing at Bartabunga that allows to propose that the actual tremor, this crackling tremor, which was always thought to be related to fluid flow, is actually not related to fluid flow at all. It's actually related to the rock breaking, and it's making a pathway for the fluids to come in. It sounds like a subtle distinction if you're not in the game, if it's not your specialized area, but it's a big, big distinction in terms of the difference between the process, what's actually happening. So that allows us to contextualize how this tremor tells us what's going to happen as a type of early warning. So buoyed by this success here, we're actually now we've just deployed equipment on Hecla through a project that Martin Mulhoff has, and it's extremely arduous field work. You put up this is a wind turbine to power stuff on top of Hecla volcano in Iceland. This is the wind turbine going up. 2 days after they put it up, they came back, and here it is, completely snowed in. And this is only this month. So very, very tricky arduous field work. But hopefully Hecla is a very dangerous volcano. It has the same issues here, and we will, we hope, be able to give much longer lead-in time warnings that are currently available on Hecla, which at the moment are about 50 minutes, 50 minutes, which is not enough because it takes hours to get off the volcano, so it's a dangerous place. So the final thing I want to touch on is this idea of physical models and data-driven approaches, the tools that we have to help us forecast. So we can think of this in two different ways. So, and I won't say they're two different camps, but they're quite different approaches. So we can actually say, okay, do we have an understanding of how the system works? And if we do, can we build a mathematical model for that and then predict what that system will do in the future? So again, the atmosphere is a classic example where you understand atmospheric dynamics and you actually predict what's going to happen in the atmosphere in the future. And that's a physical model-driven approach, where you build a physical model, a model of how the thing actually works. You run simulations on a computer to give you an indication of what the future should look like, okay? The other way of approaching a problem is to say, listen, this is so complex. So you think of the volcano stuff, and it's so complicated, I can never physically figure out what's happening. And when I say a physical model, I don't mean a geological model. I mean even a conceptual model of how the thing works. I have no idea what's going on, let's say. You think, how am I going to address this problem? One of the other ways is just to listen to the outputs from it. Listen to the earthquakes. Look at the details of the earthquakes, the frequencies, the times they arrive at, and just use a data-driven approach to say, I'm just going to pattern recognize. I'm just going to look and see what happens, and what happened in the past might help me understand what happens in the future, okay? So there's two different approaches. There is some overlap between them, but I want to just talk about both of them and show you a little bit more about them. So the examples of physical model, here's an equation which is, these equations are very, very powerful. It basically allows us to simulate acoustic wave or sound wave propagation. So what does this equation do? It basically shows you how pressure is changing with time with respect to space, how it's changing in time and space. So T is time, X and X is space. So basically, if I have a pressure wave, I can actually use this equation to tell me how that pressure wave is going to propagate. So if I built a physical model of this room in detail, generating acoustic waves, I can use this equation to calculate all the echoes. I say, no, that's too echoic. Let's move this piece of furniture there. That sounds a bit better. So you can actually use that forward mathematical model in order to do that. A very, very powerful thing to be able to do if you understand the system enough to be able to derive an equation for it like that. And so I could show you in earth science, we do this all the time. And we can simulate wave propagation. So there's like an explosion in water. This is a water layer. This is depth going down into the earth. Here's distance across the earth's surface. There's an explosion in water. The pressure goes through the water, down into the solid earth, gets reflected off all the boundaries, and comes back up to the water surface there. So that simulation is run basically on a laptop using that equation. What might the uncertainties, though? Remember, we're talking about uncertainties. So what might the uncertainties be in this type of physical modeling? Well, the uncertainty could be that we don't understand we don't capture all of the physics of the problem. And so therefore, this equation might even start by being invalid, or at least approximate. And in the example I showed you, it is very approximate. Because what I did is I used that example to simulate wave propagation in the earth. It's fine, it works fine here in the water column, because the water is a fluid and it's an acoustic wave. But as I mentioned previously, when the waves get into the solid earth, they get much more complex. And none of those are captured by that equation that I've given you. So physical modeling assumes that we understand the problem sufficiently to write an equation that captures all the physics of the problem. And that's fine for relatively simple systems, but in some systems and some of the things that are going on volcanoes, we don't have that information. We don't know enough about the system to be able to put it in mathematical form so that we can then predict what the future should look like, okay? So that is a challenge. So that's one thing. So the other example is the data-driven approach, the pattern recognition approach. So pattern recognition, it's in Matthew's Bible, or Gospel. Red sky at night, shepherd's delight. Red sky in the morning, shepherd's warning. And that's over 2,000 years old. And it's basically pattern recognition. At the time this was constructed, nobody had an idea why that was the case. They didn't care. It just worked most of the time. Now we know it's related to particles in the atmosphere and absorption of light and all that sort of different parts of the light spectrum. But at the time, nobody knew. They didn't need a physical model for it to be useful, okay, or to be even endemic in the culture. So that's an interesting one. So the question is, can we say, hey, listen, forget about all these physical model stuff. Forget about your large-scale computer simulations. We're just going to look at data, and we're going to let data tell us what's going on in the world. And that's where we are. That's the way we're heading with this big data stuff. Everybody's talking about data. So data is great, but it's not a panacea. So I'm going to show you something I really like about data. An example I really, really like, and I have to share it with you, even if I'm over time a little bit. These are seismometers in California. This is the US array, an amazing initiative where they put out thousands of seismometers. And what we're looking at here, so if you look down, this is a seismogram. There's an earthquake in Sumatra, and the P waves have just arrived through. Remember I said P? And these are the S waves are now arriving through. This is like waves. Remember I showed you the simulation of waves using that equation. This is not an equation. These are individual stations that are sitting in somebody's field, and we're just looking at the data ripping through the station, and you're literally plotting the amplitude at each station at every time step. So every 10 milliseconds, you're plotting the amplitude. And you can see amazing things. So the main surface wave has gone through. So the Sumatran earthquake's gone like that. Look at where the waves are coming from now. They're coming from the east. Now, this is my interpretation when I saw this. I don't know what's going on here. I think that these waves are being reflected off the Rocky Mountains over here. So the surface waves come in over the top. They go through the array. They hit the Rocky Mountains, and they're coming back in. But wait. When you get an earthquake, waves go in both directions. So we got the shortest path first, but now look at what's happening. Now the long path is coming across the array. This is real data. This is not a simulation. And here's the data. The surface wave that round a long way around the Earth is coming back into the array from the other side, okay? Now, here, up till a few years ago, we had to run numerical simulations to see things like that. The problem with our numerical simulations is we didn't understand the Earth structure properly. We might have been missing some physics in the equations and so on that I mentioned before. Here, everything's captured in the data. So, there's some really interesting things happening there. But as I mentioned, it's not a panacea. So I'll go on there with this. So you can see there's a lot going on here. So this is from Nature, 30th of August. Aftershock forecasts are moving to artificial intelligence. What does that mean? When you get a big earthquake, we know we get lots of aftershocks. Understanding where these aftershocks are is extremely important for the people on the ground that are dealing with the consequences of the earthquake, for first responders. Because the aftershocks themselves can knock down buildings that have already been damaged. So when a big earthquake goes off, the first thing people want to know is where are the aftershocks going to be? And you think, well, they're going to be everywhere. They're not necessarily going to be everywhere. Because when an earthquake goes off, the stress changes around it. Some of that stress makes aftershocks more likely, but some of that stress makes aftershocks less likely. And we have models, like physical models, that describe this in terms of, code, writing computer code to estimate stress transfer, to estimate all that sort of stuff, and then estimating where the aftershocks are going to be. The AI system they said with the AI system, now forget about that. We're just going to take lots and lots and lots of past earthquakes and lots and lots and lots of past aftershocks. We're going to see what happened, Here's a scenario A, this is what the outcome was. Here's scenario B, this is what the outcome was. And let the system learn through pattern recognition what actually happened. And it turns out that the aftershock forecasts from the AI system are outperforming our numerical models, okay? Why can that be possible? We're missing something possibly in the physics of the models, some detail, something's missing. And just the big data approach is actually capturing it for us. So what might the uncertainties be in data-driven analysis? Well, it's really based on the idea that what happened in the past is still going to be true for what happens in the future. So if you have a stationary system, a system where the average properties are not changing, this is fine. But if you have a system where things radically change, then you could fall foul of pattern recognition or even some of these AI algorithms, that the way they're being employed in earth science, for example, or certainly in geophysics. I'll give you a quick example. You have a large, so you train an artificial intelligence system to recognize very specific signals on a volcano, and then it's able to tell you what signals are going to follow what, because they've always done that. And then you get a very large volcanic eruption, and half of the dome collapses, like half the volcano falls away. And then the next time you get signals, they don't look the same anymore. So now you've got a trained artificial intelligence system that's completely lost because it's never seen any of the stuff it's now seeing again, okay? So so they have their challenges as well. So basically, with the pattern recognition systems, if you train an AI system to recognize the difference between a dog and a cat, and you show it lots of dogs and lots of cats, and you show, okay, what is this thing? This is a dog, that's a cat, and everything is fine. And then one day, an elephant shows up. The system goes, what am I looking at? I have absolutely no idea. Lost. So that's when you need to understand how the system works. You need to understand the physical basis for the system if the thing is going to change very rapidly. Okay, so my final slide is a conclusion. The Earth is a complex object with many interacting parts, and future states of the system with many degrees of freedom, things that can change, are not usually not certain, although they can give us short-term likely behavior, and we can estimate that. What's really interesting development in terms of public safety is a melding of technology, fast data analytics, including artificial intelligence. And really importantly, a streamlined civil authority engagement. I don't have the time to go into that, but everybody has to be on the same page with this because the time frames are very short. And so, everybody is part of that team, including the civil authorities who end up having to affect, the change, the moving people, the things that are really, really necessary. But if you excuse the pun, a certain degree of uncertainty makes the world a more interesting place. So I think we do need to embrace it. Thank you.